In this video, we're going to cover the Runge Kutta methods for solving initial value problems. The Runge Kutta method or methods is really developing. They developed Runge and Kutta were German mathematicians. They developed a general equation that encompasses all the different methods that we talked about previously for solving initial value problems. So, as we know, an initial value problem is described by the rate of change of a particular function. So I have a function x is a function of t. We're given the rate of x with respect to t as a function of x and t, and would like to know the value of x as t changes. As time evolves, we'd like to know how x changes, knowing the rate. The Runge Kutta methods give the general equation that if xi is the value of x at an initial value ti, then the value of x sub I plus 1 at time equal to ti plus 1 after a time increment h is given by x sub I plus 1 is equal to x sub I plus h multiplied by phi, where phi really represents the rate. As we mentioned in the previous methods, every different method relied on a different expression for the rate phi. The Runge Kutta method, or methods, gives a general expression for the rate as a value alpha 1 multiplied by k1, a value alpha 2 multiplied by k2, a value alpha 3 multiplied by k3, and so on, where these alphas are some sort of are numbers and k's are rates evaluated at different points within the domain between ti and ti plus 1. So these alphas are constants, and these k sub j's are the rates evaluated at different points within the interval between ti and ti plus 1, or xi and xi and x sub I plus 1. k1 is given as the value of the rate, which is f, evaluated at the initial point. The other k's are the values of the function, which is the rate, evaluated at internal points, and these internal points are evaluated according to the different equation. For example, a k2 is equal to the value of f, evaluated at x sub I plus some constant q11, multiplied by k1, which is the rate at the first step, which is the rate at the first point, multiplied by h. And the time is ti plus a constant p1 multiplied by h, and so on. As you can see, each of those k's are evaluated at different time points and within the interval. So now we're going to see how these methods, or how the previous methods all are examples of the Runge Kutta methods. For example, in the explicit Euler method, if you remember, x sub I plus 1 was equal to x sub I plus h multiplied by the rate evaluated at the first point. Basically, the explicit Euler method, which is given by this equation, is such that all these values are 0, alpha 1 is 1, and k1 is the slope at the first point. So this was the explicit Euler method. The Huynh method, if you remember, x sub I plus 1 was equal to x sub I plus h multiplied by the average of the slope at the first point and the slope at the final point, the sum divided by 2, which, when we look at it as an example of the Runge Kutta methods, we only have the first two terms. Alpha 1 is given as half, alpha 2 is given as half, k1 is the value of the slope at the first point. K2 is the slope at xi plus h multiplied by k1, and ti plus h, basically the slope at the end point. And the end point is evaluated using, of course, the slope at the first point. The midpoint method, if you recall, the x sub I plus 1 was equal to x sub I plus h multiplied by the slope at the intermediate point between x sub I and x sub I plus 1, or the intermediate point between t sub I and t sub I plus 1. And this xi plus half, if you remember, was evaluated using the slope at the first point. And so when we look at this as an example of the Runge Kutta method, we find that all these terms are equal to 0 except the term alpha 2 k2. Alpha 2 is given as 1, and k2 is the slope evaluated at the intermediate point. The intermediate point is found as t sub I plus h over 2, and the value of x in the middle is given as x sub I plus h over 2 multiplied by the slope at the first point. We're going to cover another method, which is called the classical Runge Kutta method, or the fourth order Runge Kutta method, which has the following form. X sub I plus 1 is equal to x sub I plus a weighted average of different slopes. K1 plus 2k2 plus 2k3 plus k4. These are all different slopes, and their sum divided by 6 give us a weighted average of these slopes. K1 is the slope at the first point. K2 is the slope at the intermediate point, where the intermediate point is found using the first slope. K3 is the slope at the intermediate point, where the intermediate point is found using the slope that we just simply the slope K2. K4 is the slope at the end point, where the end point is found using the slope K3. This method is similar, has an order similar to the Simpson's 1/3 rule. The local error is directly proportional to h power 5, and the global error term is directly proportional to h power 4. So you can see, while it has lots of computations, you need to evaluate the slope several times compared to the previous methods. However, it renders the computations much more accurate in comparison to all the previous methods. If you, just as a reminder, the Euler explicit and implicit methods were the order of the global error term was h, means the error was directly proportional to h. The midpoint and the Huygens method, the error was directly proportional to h squared. This method is superior, and the order term is directly proportional to h power 4. Here we're going to solve the same example that we solved before in the previous methods. We're given this rate. dx by dt is given by tx squared plus 2x. The initial condition is x when time is 0 is equal to -5, and we'd like to know how x evolves as time evolves and goes from 0 to 5. And the time increment that we're going to use is h is equal to 0.1. And previously we solved this using the different methods. Well, now we're going to solve it using the Runge Kutta method, the classical Runge Kutta method. And actually, when we solved it before, we used h is equal to 0.1, but here we're going to use h, when we solve it using the classical Runge Kutta method, we're going to use h as equal to 0.4. Alright, so this is the slope. We first start with the initial point when the time is equal to 0. x naught is equal to negative 0.5, and our time increment is equal to 0.4. The Runge Kutta method states that x sub I plus 1, which in this case is equal to x1, is equal to x naught plus h over 6 multiplied by all these slopes, the sum of these slopes, which is some sort of a weighted average of these slopes. What is k1? K1 is the slope evaluated at the initial point. X naught is 0. X naught is negative 5. T naught is 0. So substituting in the equation for the slope with x naught is 0 and t naught x naught is negative 5 and t naught is 0, substituting in this equation, I get k1 is equal to negative 10. K2 is equal to the value of the slope evaluated at x naught plus h over 2 multiplied by k1, t naught plus h over 2. Now x naught, which is negative 5, h over 2 is equal to 0.2. K1 we just evaluated as negative 10. So this gives us this value, and the time is equal to 0 plus 0.2. So this gives me a value for x, this gives me a value of t. Substituting this value of x and this value of t into the general equation gives me this, and gives me a slope k2 equal to negative 4.2. K3, which is the slope at the intermediate point. The intermediate point is found first as x naught plus h over 2 multiplied by k2. K2 is the value that we just found. So x naught is negative 5, h over 2 is 0.2. K2 is equal to negative 4.2. So this gives me a value for x. T naught plus h over 2 will give me a value of t. So this is a value of x, this is a value of t. Substituting here will give me a value for the slope as negative 4.8589. Finally, the fourth slope, k sub 4, is equal to the slope evaluated at the value of x given as x naught plus h k sub 3, t naught plus h. X naught is negative 5, h is 0.4, k3 is the slope that we just evaluated. T naught plus h is 0 plus 0.4. You can see that this is the value of the slope at the end point. This is the value of x. This is a value of t. Using those values and substituting in this equation gives me a value for k4. So now I have k1, k2, k3, and k4. I can substitute k1, k2, k3, k4 in this equation, and this will give me a value for x1 given as negative 6.51465. You can see it's a lot of computations for one value of x1 compared to the previous methods, but comes with very high accuracy. Here's an Excel table. You can try to solve this example by hand, and you can use Excel and compare your solution to the solution given here or on the website. As you can see, here we are using h is equal to 0.4. The black dots are following the blue exact solution. When the blue line gives the exact solution, you can see the black dots are following it, are matching it exactly, implying that this method is very accurate. Of course, for this particular example. We'd like to compare this visually, how this method compares to the Euler method, compares with the Euler method. Of course, for a small value of h, when the time increment is small, and we do this, whether we use the Euler method and the classical Runge method, they're both accurate, although still the Euler method is not very accurate where the slopes change rapidly, where there's a high or fast change in the slopes. When h is very high, you can see that the Euler method is losing accuracy in this area, but the Runge Kutta method is actually very accurate even with a very high h. You have this tool on the website. You can try and change h and see the effect on the solution using the Euler method versus the solution using the classical Runge Kutta method.